So I'm going to go ahead and switch over to the lecture PowerPoint for Chapter 7. So if anybody has any further questions or anything they'd like to address, go ahead and pop in the chat, or you can just go ahead and speak up, but just bear in mind it might take me a second if I'm in the middle of a statement or something. Again, this is part of my effort to kind of get lectures recorded so you can review them at your own pace if you wish. So if you're not in CTS-120 and you want to audit this, you can. This is a networking chapter, so it is kind of similar to stuff that we'll talk about in Net 125 and CTI 120. So as per most things in IT, this is a lot of interrelated stuff. So Chapter 7 is all about setting up a local network. So rather than setting up something that we would see in a more commercial or enterprise situation, this is what you would have for a small office or home office, what we would call a SOHO environment. So we're going to look at different network types as well as the connections that they use, how to hook up a standalone computer to a wired or wireless network, how to configure and secure what we call a SOHO or multifunction router on a local network, and we'll talk about what makes a multifunction router different than what we would consider to be a standard router, something that we would use, again, in a more commercial or enterprise situation, and how to troubleshoot network connections using the command line. Now, some of you may not be as familiar with working in the command line, but I'll tell you, if you're going to work in IT as a technician, it's definitely something that you want to explore a little bit more, simply because it gives you a lot of flexibility and it gives you the ability to control things in a more automated sense, being able to do scripting and automation. So the types of networks that we deal with are defined usually by their geographical coverage as well as the technologies that we incorporate. Now, in the modern environment, excuse me, where we traditionally use just fiber optics and high-end copper lines, what we consider to be broadband copper, we worry more so about the size of the network. So a PAN, for example, personal area network, tends to consist of small personal devices, just a couple of devices connected to each other in a limited physical area. So this would be something like your Bluetooth connection to your headset from your phone, or connection to a smartwatch from your phone. These devices create what's called an ad hoc network. Ad hoc basically means that there is no underlying infrastructure that has to facilitate communication. So in a standard network, usually if you're doing wireless, you have what's called an AP, or an access point. That is connected to a switch or a multifunction router. That multifunction connection then goes to an outside network. So you have kind of an underlying structure of the switch or the router or whatever you have is allowing communication between your two devices. That's what we would call an infrastructure-based network. An ad hoc network, which we would see in the whole PAN style, is these two devices essentially configure themselves to talk to one another with no intercession. There's nothing working in between them. So with a Bluetooth device, obviously, you don't need any kind of switch or router. You just have a direct connection between the source device and the receiver. With a local area network, we cover a small local area such as a home, office, or other building. So this is a relatively limited network in terms of the physical scope, but it can be very complex in terms of the logical scope. So when we talk about physical versus logical, we have to talk about the way that we see things, physical, versus the way that the computer would see things, logical. A wireless mesh network, this is going to cover an area that is geographically limited in size, so something like Cape Fear's North Campus or downtown. It's great for places where cables are difficult to install. I've seen a lot of instances of this in like downtown in the historical buildings, simply because, you know, they have a lot of plaster walls as opposed to drywall. In historical buildings, they try and modify as little as possible, so running cable behind lath or any of those other types of constructions for those walls is very difficult. There's a lot of potential for damage. So a Wi-Fi system tends to be a lot less intrusive. They also tend to use a lot of what's called PoE, power line over Ethernet, so that you can include a power connection over the Ethernet line. A metropolitan area network, or a MAN, is going to cover a large campus or city. So when I say a large campus, I don't mean something like Cape Fear, because Cape Fear is not considered a large campus. UNCW really isn't even considered a large campus. So something more like NC State. So if any of you guys have been up there, and they've got the DHL library, and covers most of Hillsborough Street, and it's a very large campus, covers a lot of geographic space. You can also have ones that, as it says in the second half, cover a city. So I've seen metropolitan area networks in areas like Charlotte, things like that, that cover a very big scope, and they're usually built as part of what's called a co-op or a cooperative agreement based on the consortium of users that manage and use it. A WAN, or wide area network, covers a very large geographic area, and it's made up of smaller networks. And this brings up an important point. The whole concept of the internet is that it is a network of networks. It is a conglomeration of several networks working in concert with one another. So let's say that everybody in this chat right now has their own internal network that they're using, because that's kind of the case. Each of those networks is called a default gateway that allows you to move from your local area network into a larger network, something that encompasses that. And there may be several layers. You may have a LAN within a LAN within a LAN, and it comes out to a WAN, and that WAN is within another WAN, et cetera, until you get all the way up to the top of the heap, which would be the global coverage of the internet. Now, obviously, you only have to climb up as many levels as you need to get to the network that you're trying to communicate with. So a WAN can cover a very broad level of geographical coverage, but the idea is still the same. We're going to have multiple LANs that come together to make these WANs, and then the WANs can actually be scaled to almost any size. So the methodology of controlling all of this communication usually falls to what we call an ISP, or Internet Service Provider. The Internet Service Provider is going to take in the information from your local system and be able to facilitate communication with other local systems to create a larger network. The more common types of connections that we see from modern ISPs are going to be DSL if we're using phone lines, and then cable internet if we're using a coaxial cable modem. You may also see fiber optic based systems, especially now that AT&T is pushing their gigapower system through their partnership with DirecTV, Google Fiber in certain areas, things like that. Excuse me. Now, ISPs have what's called an asymmetrical structure to their upload-download balancing systems. So ISPs are going to devote more available bandwidth to downloading information and less of it to uploading for the average host. And this makes sense. When you are logging into the internet on your particular, tablet or phone or laptop or desktop or game console, whatever you have, you are trying to retrieve information. You're trying to find something out. You're trying to, figure out, who did the Hurricanes win last night? Did what's the expected rainfall for this weekend? Blah 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 blah. And with the quarantine going on, increasingly the amount of news and involvement that we have is retrieving information, getting news from the outside. Now, uploading information is important, but if you'll ever notice, if you're trying to upload something to Facebook, Twitter, Instagram, email, anything like that, the speed is got a pretty large disparity. You notice that it takes a lot longer to upload than download, and that's part of this problem. Now, granted, I say problem, but it's not really a problem itself. It's not like something that's unexpected. It is an accepted limitation that if we have X amount of bandwidth, we want to devote it to what is going to service our customers in an optimal way, what is going to give them the best usage of their resources. And because most of us are trying to download rather than upload, that's the balance that they do. Now, we talked about DSL just a little bit ago. Something that's interesting is that with when DSL was first mooted, it used just what was called a symmetrical structure. meaning that the upload and download speeds were the same. There was not this load balancing. So that meant that for companies that were paying that kind of money and they had a website or any sort of e-commerce or things like that, they were able to upload information just as fast as they could download it. So that was, for them, a fairly useful idea. Up until the point where we started reaching gigabit transfers, certain companies would actually request to be hooked up on a symmetrical structure for their data transitions, especially companies that have a very large web presence. They, of course, need to be able to upload lots of information and be able to maintain a hosting or other web resource that's accessible from the outside. So that upload link needed to be strong. Now, we have a couple of different ways of measuring the information that moves from one place to another. The theoretical maximum information rate is what we call the bandwidth. So the width of the quote-unquote band is the band of frequencies. So we have a transition going from the highest frequency that can be carried by the medium to the lowest. And then if we subtract the lowest from the highest, we get the width. We get the amount of frequency that can be covered. So that's the theoretical maximum. That's the signaling maximum. The throughput of the network is the actual amount of information that we get. So at that point, we have the available deliverable data. We have a subset of that we call good put. Now, that's not in here in the notes, but it is something that we'll talk about later on in other classes, so I'm going to go ahead and include it now. It's not something I'm going to have you responsible for, but it is something I'd like you to know about. And that is just the information that we get that is usable. So you have to think about it almost like this just kind of narrowing set of constraining borders. We have the bandwidth, which is the maximum that it can handle under any circumstances. You'll almost never see that. Of course, you know, your car could theoretically go 150 miles an hour, but if you try to drive it that fast, you'd probably get in some serious trouble or injured, because where the heck are you going to be able to get up enough straight away to be able to put your pedal down that long? That's kind of what we look at with bandwidth. The throughput is what we actually have deliverable, and then the good put is what's actually usable. So imagine that your car had no waste heat, noise, or exhaust. That would be 100% efficient, which by the laws of physics cannot currently happen. Now, with this data transmission, we have a little bit of a delay, and that delay is what we call latency. Latency is the round-trip time it takes for a data packet to travel from its originating source to its destination and back. Hold time. Sorry about the delay. Apparently my wife had an issue with trying to get the door to lock. Fun times. Okay, so latency is not just the transition from source to destination, but source to destination back to source. It has to be the round trip, so that not only do we get the transmission of the original information, but we get confirmation or a response regarding that transmission. So here's just kind of a graphic to show you how the structure works. We have our local area network, which is very similar to what we'd expect to see in a SOHO environment. We've got our router and our modem. This may be combined into a single device. It may not. That communicates with our ISP, and then the ISP is responsible for facilitating communication to the internet at large. So when we compare cable internet and DSL, we have to look at what's called signaling types, how information is sent across a particular connection. So both of these modern technologies use what's called an always-on approach. It used to be when you had a telephone line for communicating on the internet through what was called dial-up or POTS-based internet, you had to quote-unquote dial in. There was an access number that you would quote-unquote call using your modem, and that would initiate the data transfer. And that was that really obnoxious noise that everybody talks about. That sounds just like some weird, robot tones. And that was exactly what it was. These were tones that would essentially initiate, okay, now we're going to go ahead and switch this thing over from voice to data to be able to send information back and forth. And any pulses that we send back and forth are going to be information that is communicable as data, not as voice. That's why if somebody picked up the landline back in the dial-up days, it would throw things off, because all of a sudden there was voice or audio noise being introduced into the line. So cable internet uses existing TV cable lines, which we've had introduced into our home environments since the 1970s. And the PC and data signals coexist. They live on the same cable. What we do is we just change the different bands of frequency, and again tying back to bandwidth, where these data signals live versus where the TV signals live. So upon receipt of the base information, the cable modem takes the digital information excuse me, of the PC signals and separates it from the digital information of the television signals. So that's why you have a what's called a tuner box. So even if you don't have DVR service, if you have Spectrum or Charter or whatever else, you probably have a box that is there that has to be set up so that it can interpret information coming through from whoever your provider is. If you don't have a box, you're either using what's called over-the-air digital signal coming through an antenna, or maybe you have a smart card that is built directly into your television that interprets those signals. But in any event, you still have to have some kind of intercession between your device and that ISP, that service provider. Now, if we have any information coming in that is digital, there are situations that it has to be converted into analog, and then vice versa. If we have a digital signal that's being sent out, it has to be converted to analog to be able to go over copper lines, because digital signals have to be done with specific types of voltage transmission, and then analog is what we use to transition over cables to be able to move it from one place to another through digital cable lines or whatever else. DSL is based on standard telephone service, but uses a different form of signaling to optimize the speeds. It uses the unused voice frequencies, and when I say that, be aware there's a ton of frequencies that are unused. If you look at what's called wave format for an audio file on your computer, if you were to use like Windows Sound Recorder or anything like that, and you were to save it as a wave, that would be kind of what we call raw data for audio. It doesn't have any compression. So that means that it samples at 44,100 kilobits per second. So there's a lot of information being captured. Now, the human auditory range only goes from 20 to 20,000 hertz. So the sample range that this thing is picking up is easily twice what your ears can actually perceive. So that means that there's a lot of space that isn't even being used. And then there's more frequencies beyond that the copper phone lines can support. So that unused space can be used instead for supporting these data transmissions. Now, because we are separating those frequency bands, and we use what's called a DSL filter in order to move information to and fro, we're able to use the same line for voice and DSL simultaneously, which was not something we were able to do with dial-up. We had to dedicate the line. Now, when we're deciding between cable internet and DSL, unless you have a very limited specific need, almost always you're going to go for cable internet, just because it's everywhere, and B, it tends to be the most versatile. Now, if we have an issue such as limitations for cost, maybe cable lines haven't been run where you are, but phone lines have, that might be something. And you do have to worry about with cable modems that you are sharing your infrastructure with other users in the same space. So let's say that I live in an apartment. I'm in my apartment right now. Excuse me. I have several neighbors that all use the same cable service because that's part of the arrangement. The infrastructure is that we have a little bit of a monopoly when it comes to cable service. So that being the case, we're all using the same cable lines. If everybody starts using, ultra 4K Netflix at the same time, we may see a degradation in that signal because everybody's basically on the same connection at the same time. Think about it like if you had one big water pipe and it had three spigots into it. So if you opened it up, the water starts coming out of one. If you open up the second one, water will also flow out of that one, but the pressure will be slightly less. If you opened up the third, the pressure, of course, would then reduce yet again because there's a fixed amount of pressure that can come through at any one time. So very, very similar to what we see with bandwidth on that kind of infrastructure. Now, it's a similar setup for both. You have your cable line or your phone line connection that comes in. There's a junction box that it attaches to, and that's usually where the primary filtering will start. It'll amplify the signal, send it to the cable modem or other differentiation tool, and then it will separate it into phone and data signals separately. So this is an example of a DSL filter. You can see that it's labeled on the jack itself that there's a separate connection line for where the DSL connection goes versus the phone line, and then you see the actual plug-in filter that goes over here on the side. So this is the back of a cable modem for comparison. So you can see here that we've got just two phone lines. There's not a lot of quote-unquote bells and whistles. Whereas here we have a set of things. We've got like an Ethernet jack here. There's this big yellow cable. That's the connection that goes to our data infrastructure on our PC or whatever device we have. We have a reset button because there are some internal settings we can manipulate. There's our coax connection. We use a BNC connection there, usually just a screw-on cap. There's our power connector. There's our serial number, usually our MAC address. And we can see here over on the far left side, these two RJ11 connections, those are going to give us phone lines. So if any of you guys had Time Warner Cable or Spectrum or Charter or whoever with telephone service, you often had your cable modem hooked up to your phone line, so that way you had digital voice. And it was very cool because digital voice was a lot more crisp, a lot more clear, so you didn't have any issues trying to kind of get the fuzz out, as it were. Certain phone lines, depending on interference or whatever else, can get very cloudy in terms of quality. With digital voice, it was definitely a lot more qualitative. It was easier to appreciate, better quality sound. Now the problem was, if you had an emergency, for example, and your phone lines were down because you had no power, then you would have no phone. Whereas in an emergency, I remember during, I want to say, Hurricane Fran, I was sitting in the kitchen of the house that my parents had at that time. I want to say I was a teenager. I was like probably 12 or 13. And I was sitting downstairs in the breakfast nook, just hanging out. I had this little, I don't want to say fort, but I had this little zone that I'd kind of camped out for myself. I had a lantern. I had my boom box that was powered by D-cell batteries. And I was able to pick up the landline for the house and call into the radio station. I was listening to Surf 107. I missed that radio station a lot. And be able to request certain songs. I was able to ask them to like play Tool or whatever else, because of course you don't sleep normally during those kinds of situations. So it's like 11:30 at night, and I was like, all right, man, I need something to kind of help me zone out. So I put on 46 and 2, and that connectivity does not exist if you're using a broadband-based telephone service. Now, of course, people will argue, well, you've got your cell phone, and that's true. But the idea is that even if you had no power in your house, which I did not at that time, I was running entirely on batteries, you still had a connection to get out in case of the need for emergency services. Even if my cell phone battery was dead, which I didn't have a cell phone at that time, I would still be able to connect to emergency services and get help if I needed it. So if we have a dedicated line using fiber optics instead of copper or telephone lines, we have what's called a dedicated PTP connection. We have a point-to-point dedicated line that goes from our source to our destination. And this is because fiber optic uses light pulses and is able to facilitate a number of connections on the same cable without having that overlap, without losing signal integrity or signal strength, achieving what's called a lack of attenuation. On a fiber optic line, something that is very, very thin, usually the size of a pencil, if not thinner, is able to handle voice data, internet data, and television data for hundreds of different houses. Now, your upstream and downstream speeds may vary, but you'll probably see a significant speed increase versus going through a cable or DSL connection, DSL probably being the lowest of all of them, simply because of the limitations of a copper line phone system. And then, of course, going all the way up through cable kind of being a mid-range, and then fiber optic being the most powerful, but definitely the most expensive. Now, granted, those prices have kind of come down over time, but they're still very spiky in comparison to working with, for example, just a very basic package with Spectrum. You can pay like 40, 50 bucks and have good signal. Of course, right now, anybody who hasn't had cable internet and they were a K through 12 student, or I think a college student too, they have those connections. They have free available right now, just to make sure that everybody has connectivity during the pandemic, which is kind of neat. But again, yes, based on your speed, the higher it goes, the higher your prices are probably going to go. An interesting thing that I've run into is that the upstream to downstream ratio doesn't really scale. So let's say that you've got the 300 megabit downstream package or the 600 megabit downstream package from Charter or from Spectrum or whomever. Your upload speed is probably still only going to be 20 to 40 megabits per second upstream. So download, very, very fast. Upload, not so much. Still very interesting, simply because a lot of home customers do not have a need for uploading that kind of information. So of course they're going to say at the ISP, we're going to go and limit the amount of connectivity that we're going to provide in that case, so that we can have more customers on the same connection and not lose extra information. Now, satellite, this is another option. It's not a great option, but it's another option. This provides high-speed internet connections, and I use that term very loosely, in remote areas. It's available everywhere. If you have a line of sight with the sky, you can connect to this. So airplanes, that's totally fine. Rural areas, doesn't matter. Now, whenever we're dealing with satellite, we have to be aware of what's called line of sight connectivity. And I know they've misspelled it here, S-I-T-E instead of S-I-G-H-T. Again, that's Cengage, that's not me. And latency when uploading. So of course there's a bit of a delay. So as you might guess, certain applications like teleconferencing or multiplayer gaming that would require a very quick internet connection to be able to respond in a very frantic environment are not going to be present. So that can give you some problems. As I said a little bit ago, they also call dial-up what's called POTS. Now, POTS is an abbreviation for plain old telephone service. It is the slowest connection. It is the most widely available. But, for certain things, for like credit cards, just what we call merchant services, it works just fine. And the fact that you can pay like as little as I think like $5 a month for a very basic dial-up internet service, that's pretty hot. If you don't need internet for anything else for your particular business, and you can still have that connectivity in the event that you need to process a certain type of payment, that's perfectly fine. Now, of course, with the modern situation that a lot of people deal with of having like a Square reader or something else built into their phone or other mobile device, that even will start to go the way of the dinosaur. A cellular WAN, a wireless wide area network, WWAN, covers a very wide physical area, very much like a WAN does. This is just going to use a wireless connection instead of a wired one. And it's made up of what we call cells created by base stations. Now, these cells tend to be hexagonal in shape. So like a honeycomb, it's going to have 6 sides. And I say that in a very rough sense. but they're structured to kind of approximate a circle, but there's a different direction in which each antenna will project. So it tends to be represented as hexes. Now, a base station is almost always going to include more than one transceiver and antenna on the same tower. So it's going to be able to support multiple technologies. So let's say that it has tower support for both Verizon and for Sprint. So that tower is built cooperatively to use the same physical space to be able to cover different provider networks. Now, two technologies that we see a lot when we talk about cellular coverage are GSM and CDMA. GSM is Global Standard for Mobile Communication, and CDMA is Code Division Multiplex Access, or multiple access, depending on what definition you look at. But the idea is the same. So Global Standard for Mobile Communication is pretty self-explanatory. That is the global cell phone standard, if you will. So when in the 90s, if you wanted to use what was called a world phone, you had to go through a company that supported GSM standards. At that point, that was T-Mobile and AT&T. If you wanted to go through Verizon or Sprint or any of those subsidiaries, you used what was called originally TDMA, Time Division Multiple Access, or CDMA. So the idea is that you would use either different code numbers or different intervals of time measured in milliseconds to be able to interleave different conversations on the same physical transmission point. So being able to set up, maybe a dozen communications on the same tower, you would have to say, okay, every, 110 milliseconds, or it wouldn't even be that, it'd be more like every 5 milliseconds. I'm going to go ahead and flip between one signal and another, and the delay that your ear would perceive would be incredibly low. Long-term evolution, LTE or VoLTE, these are two different technologies related to one another that help to support what are called the base 4G technologies. So long-term evolution is meant to cover a number of different technologies blanketed under the terms of 4G. And then you have 5G LTE, where they're still using the same general technologies, but including some major revisions. And for those of you who have read it all over, 5G does not cause cancer any more than any other type of cell phone radiation. It's a new suite of technologies that is used to increase the speed of wireless technology that is available to us. And it is a pretty substantial increase in speed. So to connect a computer or other device to mobile broadband to a cellular network, we have to have the hardware to connect, so that's our physical adapter. Then we usually have to have something that tells the network that our traffic is supposed to be allowed. And that usually comes through like an RUID, or in this case, a SIM, subscriber identification module. So for those of you who have fiddled about with your phone, I'm sure you've seen this little plastic card I'm sorry, in the back of the battery compartment, or possibly on the side tray if you have like an iPhone, that has this little the metal contact plate on it, a little smart contact plate, very similar to what you would see on your bank card. That connects to the device and says, this is my, almost like a license plate to say this is who I am, so that means that this particular connection is legitimate. This person is being identified by an external module, and we can verify that their account is in good standing and that they have access to these particular services, whatever they may be. So some different things that we may see once a device is connected would be like an embedded mobile broadband modem, what we call a hotspot in certain cases. And then we have cell phone tethering, where we take the USB connection that we would normally use to charge the device and connect it to a laptop or other USB capable device that would then be able to borrow, if you will, that data connection and be able to use that instead of a Wi-Fi signal or something else. A USB broadband modem, these are also what are called cradle point modems. You would see these from companies like Sierra Wireless, things like that, that would plug in, and they would act as a modem slash antenna using USB. LTE installed internet, maybe it would be something that was built in rather, as a chip on board of the device. And then you can have just a standard mobile hotspot that you could run from something like a cell phone, or in certain cases there was the I think the drive on module. This was a hotspot that plugged into the OBD2 port on your car and provided mobile Wi-Fi while you were driving for people in your car. So if you were a parent who had kids and you wanted to make sure that they had access on their tablet so they could watch, Mickey Mouse Clubhouse or whatever else, that's something that you could then invest in. That might make it a little bit easier rather than having to hotspot your phone or consistently, downloading information, or have to have their tablets be connected via a Wi-Fi interface that was generated through cellular. So as I said, cell towers tend to be represented hexagonally simply because it's just an easy way of being able to divide up the space that these devices would cover. Here is our SIM card slot. So if you look right in the middle of the image where the back of the phone is, and you can see the stickers for the MEID. I'm trying to remember. It's the Mobile Electronic Identifier, I believe is what that stands for. If you look up and to the left of that, you'll see where the arrows point. That's what's called a nano SIM. It's a very small one. There are also standard micro SIMs that are a little bit bigger than that. And then there's a full-size SIM card, which looks to be about the same size as your thumbnail. They're all the same thing, I will tell you that. Whenever we had people come in who had issues with, we got a new phone, but I've got an old SIM card, we had a punch that we would use that we would just basically clip the edges off and be able to move their SIM card to a new device, provided that you didn't cut the metal surface. Everything else was good. So it's just the size. So a SIM card has the same interface regardless of whether it's a full-size SIM or a nano SIM. There's our tethering interface. You can see it's connected to the laptop via USB to this Motorola. There's one of our cradle point USB broadband modems. You can see that it's got a pair of indicator lights, very much as you would see on a standard NIC. So it tells us, A, it's got power, and B, that it has traffic moving across, so that it's able to identify you don't have good connectivity or something else. Those indicator lights will help you to troubleshoot that. Now, to connect to a local network, it's usually pretty easy. We just go ahead and, in the case of a wired network at least, you'd usually just plug it in and everything else is done for you by your operating system. So let's go ahead and go back a little bit and get a little more granular with it. Excuse me. If your system is not pre-installed with a network adapter and the correct drivers, you have to make sure that the adapter is correctly installed, meaning that if it's USB, you plug it into a port that has the correct speed and accessibility. If it is a PCI card, it gets plugged into the correct connector, etc. Once that's installed, remember that we have our drivers. We've got that software that has to communicate between the hardware and the operating system. Now, if it's a wired network, if we've done everything correctly with the adapter itself, we should be able to just plug in the cable from whatever our source is, if it's the cable modem, if it's the wall jack, if we're in a building that already has wiring for Ethernet. In any event, we have a connection between the two devices. We plug it in. And as I said, for the little cradle point modem, you should be able to verify the connection lights. So you should see one for power, then you'll see one for network traffic, and it'll usually go from yellow to green. Now, because it's a very particular shade of yellow, they usually refer to it as amber. It's got kind of an orangish tone to it, so just bear in mind that if you hear somebody say, are the connection lights amber or green, they mean yellow, but it's just, again, in certain industries we have a level of communication that's sometimes slightly more detail oriented, a little bit more uptight, if you will. Now, for a wireless network, we have to make sure that we have a wireless enabled NIC, network interface card. Once we do, thankfully, if we're in Windows, I'm going to try and be Windows centric here because that's most of what you'll see. You'll have a network icon that comes up in your taskbar, your toolbar, or something else that will show that network connection is available. You can go and click on that, and then you can go ahead and select your network. Once you've selected your network, you click connect, and depending on whether or not you have a what's called a PSK, a pre-shared key, or if you have an enterprise login that requires a username and password, or if you have a key fob authenticator or anything like that, you'll provide your credentials, and then those credentials will allow you access to the network if correctly entered and configured. Now, if this is the first time you've connected to a local network, there's some privacy stuff that'll pop up. It'll ask you if you want to make the PC discoverable. This means, do we want to show what's in that particular device to anything else on the network? And if we're on a private network, sure, you can do that if you wish. That's how you can access things like printers or scanners or other computers that might be sharing things over that network. If you are on a public network, you're going to want to click no, because if you're visible, then other people are visible, and that could mean possibilities that people would try to snoop on or steal your data, which is a very no bueno situation. You don't want to be doing, banking on the free Wi-Fi at Starbucks, that sort of thing. Now, once we've got all that connected, let's go ahead and open up our internet browser or some other connectivity method and verify that our system is correctly connected to the network. We're able to retrieve whatever information we were expecting. In some cases, you may get what's called a capture or captive portal that pops up in order to enter a passcode or agree to terms of use or things like that. So if you do the Surf CFCC guest Wi-Fi at school on campus, you will see that we do have a captive portal that says, okay, if you're going to use our Wi-Fi, if you're going to use our network, you have to agree to our acceptable use policy. And that's not uncommon. Hospitals do the same thing. On a private network, we want to make sure that the network resources that we expect to see are available. If we don't know what we expect to see, sometimes even then poking in there and seeing what shows up might give us a better idea of what resources we could have access to. If we need to change any security settings, we're of course going to go into the Settings app and then go to Network and Internet or the Network Sharing Center and be able to modify our connection properties there. So let's say that you connect to the network and you accidentally type in the wrong password. That would be where you could go and modify that. So here we have a network interface list. You can see on the left-hand side it says network on the little header, and then there's sublines for all M1, MJ West, Lenovo, TS Client, etc. This is just Ms. West, our author, showing us her network resources that are available, and it shows up the same way as any other folder. Now, if we have a wireless system, we need to go ahead and check the status of the connection in certain instances. If we go to the Network and Sharing Center, we can click on Change Adapter Settings, and the Connections window will appear. And then we can right-click the Wi-Fi connection that pops up and go to Status. At that point, we can go to the Security tab and check our passcode and all that other stuff. If we're having issues making a connection, we can reset it, basically by clicking Disable and then Enable. If we click on the wireless network and go to Disconnect, or on your phone, it may say Forget this network. That is also an opportunity for you to be able to retype your password. So here we can see kind of getting in and being able to view the various things. So we go from network connections on the left to Wi-Fi status in the middle to the network properties on the right. Of course, here we see that Ms. West is a Star Trek fan with Make It So as her network security key. And here we can see right-clicking an enterprise connection or any of the others would give us this list of options, this dialog box. We can see Disable, Connect and Disconnect, Current Status. We can bridge connections together, rename, change properties, etc. Now, in the more modern era, especially in the world of telecommuting, that has become a lot more prevalent now, as you might imagine, we have what's called a VPN, Virtual Private Network. So a virtual private network is going to use what is called tunneling in order to provide a secure connection that would represent moving from a local site to a non-local site and still trying to provide access as if though we were physically on site for those resources. So if we had, I don't know if you guys really access this yourselves, but on campus, if I log in on my computer, there are certain things that I have access to on the school intranet, not internet, but intranet. And that is a local-only resource for employees and I think for students as well. I think there are certain things you can only access if you're on campus. But there are forms that I sometimes have to fill out that I can pull from there. There are shared resources, things like that. In order to access that from home, I would have to be able to create a VPN. And the VPN essentially is going to create a direct connection from my connection at home to what would have been my connection on campus. So being able to facilitate that as if I were physically present. This can be managed by your operating system, routers, by physical hardware, or by third-party software. So it uses a slightly different form of encapsulation than we would on a standard network. Depending on who's hosting your VPN, the directions may be a little bit different. Certain VPNs may allow you to get excuse me, a particular profile, which would then allow you to use an alternative. So I use a VPN through a company called VPN Unlimited. I got a lifetime account with them for very cheap a couple of years ago on Black Friday, and it works great. And I was able to take their connection profiles, modify it slightly, and be able to use it with OpenVPN, which is a little bit more secure, a little bit less heavy on using a GUI. It's able to do things through command line, so I can include a great deal more as far as security goes. And that's perfectly fine. So again, the information is not necessarily restricted to just that one company. So to set up a VPN in Windows, you can see that we can go through connecting to a workplace through the new connection window, and then you'll go ahead and enter your VPN information. This will usually require some credentials that might be a little bit beyond the standard user, but thankfully when you purchase a VPN system, there's usually an FAQ or an instructions list that'll help you to walk through that more comfortably. Now once that is set up, you should be able to go to your network and sharing center or your network icon in the corner and be able to change over to be able to get to that VPN connection rather than using your current local connection. Now, of course, if you have the wrong authentication protocols, so if you're supposed to be using 802.1x, or if you're supposed to be using, whatever authentication you need, if you set the wrong one, obviously it won't hook up. So occasionally you'll need to be able to change that. So the properties of the VPN connection, as we saw here, going from the connections to the status to the properties, very similar in terms of how we make these modifications. You can see advanced settings down here on the bottom right. That is likely where you'd see something similar to working with a VPN setting to change that. It's just a little bit different with VPN because obviously those connections are going to be a little bit more complex. And then it's going to change, based on what protocol you're using and whether or not you have multi-factor authentication, etc. Now, if we're setting up a dial-up connection, very bare bones, you'll have to provide what's called an access number. So you'll go ahead and you'll enter your ISP information to say this is my username, this is my password, and this is the number my modem is supposed to dial to gain access to my data connection. Once that's set up, the dial-up will go ahead and go through. The modem will actually call up the ISP, and your computer speakers will actually make that obnoxious noise and be able to get your connection up and running, we hope. So we can see here Ms. West has a connection through Earthlink, so we can see that she's got her username and password there, and then she's got her dial-in access number, and then if she clicks dial, that will process the connection there. Now, something important to notice is that with different types of connections, be it VPN, be it standard, wired or wireless or dial-up, we have to worry about not only the access method, how we get onto the ISP, but once we're connected, how is our computer or other device identified on the network? Because we have to have unique identification. We can't have anything going on to where a system is not unique, because if that's the case, it won't connect. If there are two devices that have the same network address, you have what's called a collision or a mismatch, and it will kick them off so that you can't connect. So that's not helpful. So we do this usually by means of what we call an IP address. So when the connection is first made, we assign this IP address based on a pool of accessible addresses given. There's a couple of different ways we can do this. We can use what's called DHCP, the Dynamic Host Configuration Protocol, which does automatic assignment, or we can have these put in through what's called a static configuration, where we type it in manually. Now, if we have an IPv4 address, that's going to use a 32-bit string of binary numbers, which are then written as four what are called dotted decimal numbers, 0 to 255 in 4 separate blocks. If we use the 128-bit string, that is a 64-bit address, that's going to be 32 hexadecimal characters put all together. So it says here 8 hexadecimal numbers. It's actually 8 blocks of 4. So here we'll go ahead and take a look at the IP address first for IPv4. You can see here that the numbers, each in the example, 192.168.100.4, are all between 0 and 255. So that's our minimum and maximum. When we look at the subnet mask, we can see that 255 is in 3 of the octets with a 0 at the end. Now, a subnet mask has to be all ones up to the first 0. After the first 0, everything has to be a 0 after that. There's never a point where a subnet mask will stop and start in terms of the ones that are involved. And that's because when we combine the subnet mask with the IP address, we should get what's called the network address. That network address allows us to identify whether or not 2 IP addresses are on the same network or not, so they can share information locally. We have what's called a default gateway that we have to include. The default gateway allows us to move outside of our local network and communicate with other devices. This allows us to access things like the internet. And then sometimes this will be automatically assigned. Sometimes this will be statically assigned, what's called a DNS server, domain name system. This allows us to take something like the text of www.google.com and convert it into an IP address, or what's called a URL, that could be identified uniquely and be able to connect to that resource. Human beings are really good at being able to remember names, but not so great at being able to remember strings of what seemingly random numbers. So at that point, it would be easier to remember Google as opposed to remembering, 212.15.12.8. I'm just making up numbers that would fit. That's not necessarily a public IP for Google. Now, if we type in this information manually, that creates, as I said, what's called a static IP address, which means that as we move from system to system, that information will not change. Now, if instead we use what's called a dynamic IP address, there are situations in which we will have an IP address that can change based on the physical location of where we are. If we move from network to network, as long as we have the authentication credentials, our IP address, subnet mask, and default gateway may change. Now, in order to set these up, just as we saw a little bit ago, we were looking at dial-up, we're going to go to the Network and Sharing Center or Network Connections window, multiple names for similar things. And then we're going to go to our network connection in question. Maybe it'll be something that says like Ethernet, or it'll say LAN 1. There's any number of different connections there. And we're going to go to the Properties tab. Now, we're going to select our IP version. Is it IPv4? Is it IPv6? It's largely immaterial. Both of them will work. It just depends on what type of connection we're trying to hook up to, whether or not it will be the most efficacious. In any event, the default is traditionally IPv4, so we're going to go with that first. We'll go ahead and hop that in, and then we'll go ahead and type in whatever we need for our dynamic, or for whatever we need for our static address. Excuse me. If we want to use dynamic addressing, we just leave the default on, which is to select DHCP. It'll be a button that says select this IP information automatically. So here we see that the IP settings are currently on manual. If we had them on automatic, all of these boxes would be filled in for us. Now, if we're using a laptop or other mobile computing device, and we want to make sure that we are able to move from one network to another without having to constantly make changes, we can create what's called an alternate configuration. So we can have more than one IP address configured for our system. And this means that we can go in and we can have DHCP set up, but that alternate configuration means if DHCP fails, it will go ahead and try and use this alternate configuration to let us get to our static IP information. So once all that's set up and we hit OK, we can save it, and we can have multiple networks that we can connect to using the same credentials. So if you guys have a situation where you have typed in your username and your password for the Cape Fear network, and it connects or disconnects based on whether or not you're in physical proximity, bear in mind that is not a static configuration. That is your DHCP-based configuration. But faculty, in certain cases, depending on whether or not we need to be able to access a particular server or virtual machines or anything that has an external facing IP address, we may need to use static IP so that we can connect to it based on whether or not we're physically present in the same network area. So here we can see automatic addressing being selected versus user configured for our alternate configuration. Now, if we're connected via a USB connection, if we're connected via external device or a NIC, meaning that we have our wire connection through an RJ45, we have a couple of different changes we may need to make depending on the features that we wish to take advantage of. And on an adapter, we of course have different drivers that are going to be engaged or disengaged based on what features we need. And based on those changes, we may have different Ethernet speeds. Now we have what's called full duplex and half duplex transmission. Full duplex is like a telephone call. We're able to send and receive information at the same time. And that can be good, that can be bad. You can have a lot of stepping over. The only time it really becomes quote unquote bad is if we have a mismatch where one is connected to full duplex, one is to half. Half duplex only works in one direction at a time. So we have, I can send, and then I have to wait, and then I can receive information, as opposed to full duplex, which can do both at the same time. There's also what's called simplex, which is where we can only send or only receive. It's a bit more like a radio station. If you have a radio receiver, you can only receive information from the radio station. If you're a radio station yourself, you can only transmit. Every network adapter has to have an identifying number called a MAC, Media Access Control Address. This is a 48-bit unique ID number hard-coded by the manufacturer. Now, the first half of this number, the first 24 bits, is what's called the OUI, the Organizationally Unique Identifier. This is able to tell you who made the NIC that you're using. The manufacturer in question could be somebody like Dell or Broadcom or Belkin or whomever. The second half is what's called the interface ID. So the first half tells you who made it. The second half tells you this is, ID number, 3844, made by, any of these different manufacturers. Things to be aware of on your adapter when you're looking at it would be your status indicator lights, as we talked about for your cradle point modem, talking about for pretty much anything. Just be aware of whether or not the network seems to be functioning normally. Wake on LAN. This is a very handy function that when a computer receives a certain amount of information, it will wake up. So very much like when your computer's kind of asleep and the screensaver's going, and then you come in and you move your mouse, it wakes up. This is a very similar thing. This is where maybe your computer acts as a print server and is receiving information from another computer in order to print a particular physical document. Quality of service, or QoS. This is something that is much more common in modern devices, modern routers, if you will. This is going to control application priority on the network. So let's say that you have 5 or 6 different applications all doing different things that have network connectivity. But there's one, very much like this whole virtual classroom thing that we're doing right now, that needs priority. It needs to be able to make sure that it is bringing a high quality of delivery while it's working. And that kind of prioritization is done through QoS. It's going to go ahead and say, I'm going to take this particular Firefox window and I'm going to put its requests in a higher priority. So if it pops up and says, hey, I need these resources, it will be able to kind of fast pass around other connection types that might be present. Now, for a SOHO network, small office, home office, as you'll recall, we have to be able to understand what functions the SOHO provides us and how to configure them correctly. So based on what we've talked about in the previous 20 or so slides, we may have to change certain settings around, or we may thankfully have one that's pretty easy to automatically put together, provided that we've given the correct credentials. So a router, in simple terms, is just something that allows us to get traffic from one network to another, from an internal network to an external network. Okay? So a SOHO router is going to combine the functions of a router, a switch, a DHCP server, a wireless access point, a firewall, or possibly an FTP server. So all of these various components we talked about before may be incorporated into this multifunction. So the router allows us to move traffic between internal and external networks. The switch allows us to deal with traffic that's local. DHCP server allows us to automatically assign IP addresses to the correct requesting device. Wireless access point allows us to connect wireless as well as wired devices. Firewall is going to be able to filter traffic coming in to make sure that nothing malicious is able to get through, given correct configuration. It's all going to depend. And then if we use, again, the FTP functionality, then that is going to mean that we can hook up our some form of storage source and be able to share information across the network or even outside of our local network, depending on the router configuration. Now, when we're placing a router in the physical space, we have to think about physical security, because if somebody can actually get a hold of the router physically, they could possibly reset it or be able to hook into our network, which would allow them access to things that they should not have. So in general, they recommend that if you're in a business situation, that you have it behind a locked door that's only accessible to authorized personnel to prevent just random people from being able to get in and mess with your router. Now, excuse me, if we're trying to set up a Wi-Fi hotspot, we have to make sure that it is placed in an area that will provide the optimum coverage. In certain cases, you may take a router that doesn't have Wi-Fi capability and then hook up an external access point to it. At that point, you can say, okay, I've got an access point, I've got a router, I can run a cable of a certain length and move it to a place that has better coverage, and that will work just fine. For routers that have external antennas, the recommendation is that you move the antennas to a vertical position for being able to have optimum coverage. In certain cases, you may want to move them around a little bit. Again, that's just experimentation. You'll more often find that if you change the basic signal that the Wi-Fi router is using, that's going to be better than moving the antennas. You can, in certain cases, actually replace the antennas with ones that are certainly a little bit more large, or in certain cases, you can add extension cables to be able to move them further apart to give you a broader coverage range. Now, if we're setting up a router, we usually need a couple of pieces of information. Of course, we need user configuration to be able to provide credentials to say we are who we say we are. And then we can go in and make modifications such as updating the firmware. We can change the default passwords. Every router is different. So you may want to go onto YouTube. You can go online and look up the manual. There are several different places that you can try and find information about how to configure your router to best serve your purposes. Once that's done, you'll want to make sure that you save your changes, again, making sure that you're aware of what it is you're doing, and then you'll go ahead and log out. Now, in certain cases, your router may need to reboot, or it can go ahead and apply the changes on the fly and allow you to update your connection. So here we can see the interface for an R7000 router, and you can see there are several different interface sites that are here. You've got your internet connection. We've got FBI surveillance van as our SSID. That's our broadcast name for the network, the number of attached devices, guest network, whether or not we have an FTP share available via USB, and hey, there's even a firmware upgrade available up here at the top. So several different things that we can connect to be able to find the right information. Now, these are just some random things that they put in that might be things that we change to make the router a little bit more amenable to our needs, I will always recommend the first one, changing the router password. You want to make sure that if it came with a default password of any kind, even if it seems to have been randomly generated, that you change it to something more complex and more personalized to you. Yes, Connor.
Hey, I have a question for you real quick on due dates, actually.
Okay.
What lab are we on?
So the in-class labs from Blackboard are being discontinued for the moment,
Oh,
and
thank
we are
goodness.
doing just the MindTap ones at present.
Okay.
Yeah.
What about exam 3? Is that graded and done?
Those are in the process of being finalized right now. I should have those done by midweek.
Okay, 'cause I need to talk to you about that after this, I guess.
Okay. All right. So other things that we've got going on would be MAC address filtering. In certain cases, we may not want to allow a particular device to connect, so we can use what's called whitelisting or blacklisting. Whitelisting basically says everybody's blocked except for the people that are approved, and blacklisting is this particular device has done something that we do not want to allow to connect to our network, so we're going to go ahead and reject their connection at any point. So we just kind of, it's either innocent until proven guilty with a blacklist, or very exclusive with a whitelist. So your firewall is going to essentially be able to examine messages on the fly coming from the internet to say, should this be allowed, should this not be allowed? And we use a set of different rules to make this decision, quote unquote. Because remember, a computer is not intrinsically intelligent. It has a set of rules it has to follow. So we can identify this based on the particular port that's connected to, or whatever address it's trying to access, what type of activity it is, etc. To allow what's called unsolicited traffic, stuff that we did not initiate, we have to modify the firewall in order to allow that in. I will say that there are very few situations where I have felt the need to do this modification. Generally, any kind of quote-unquote unsolicited traffic, I just leave blocked. I only allow traffic from things that I know need to be connected. Exceptions for this can be used through port forwarding or port triggering, or what's called a DMZ. DMZ is an abbreviation for the term demilitarized zone. It's basically a gap between two firewalls that allows you to have kind of an air gap in between the outside network and your inside network, so that if there is any kind of breach that occurs on the first firewall, you can have that that split. Okay, so Sean's got a question. Is there a huge difference between standard routers and a mesh router like the Eero? So with those, mesh routers have a different connectivity system. Instead of using the single point-to-point connection, it uses a multiple access point system and connects them all under an SSID, the same SSID rather. So whereas if you're using like an extender or a repeater, you'll often be able to see that repeater indicated. So the difference is basically in how the work is grouped together, Sean, not necessarily in how it connects. It's just how logically these things respond to one another. So imagine that you have a 48 port switch, and there's like 12 access points. They're all connected to the same base port, and they're able to communicate with one another very smoothly, so they're treated as part of the same network. When you get into net 126 and 225, you start talking about what's called trunking, and that is something that is similar to what you'll see with the Eero, to where these VLANs that are created allow intercommunication as if they were all extensions of the same network. So things like the Eero are a little bit more efficient, a little bit easier to work with. That's really the only major change. Good question, though. That is something that is not exactly immediately apparent to the modern consumer. Something like Orbi or Eero or some of the Unifier Ubiquity materials, it doesn't exactly tell you why they're different or why they're better. It just says, hey, buy our shiny new box that has the thing, whatever the thing is. So here we have limiting internet traffic based on port controls. This is a very simple representation of when we're delivering information from an outside source to a local source. On the left-hand side, we see that there is an email server listed at port 25. On the right-hand side, we have a web server listed at port 80. So we have IP address 138.6030.5. The TCP packet says this is for 138.60.30.5:80. So the colon is basically just a reference number indicator that says what's coming after this colon is the program that essentially is requesting or is assigned this particular item. So in this particular information, let's imagine that we have a web page that we're connecting to. The information that it's delivering doesn't necessarily need to be delivered to our email server. So including the port number 80 allows us to say, oh, this is where this particular traffic is supposed to go. And then there are port modifications to where, you know, if you're on a browser that has multiple tabs or multiple windows open, you want to make sure that if you have a transaction for Amazon on one screen and you're on eBay on the other, that the purchase information that you just used for one doesn't bleed over into the other. So these ports help you to separate that information. So port forwarding, as we talked about dealing with traffic and all that other kind of filtering with firewalls, is when we receive a request for information and we move the request from a particular connection on the firewall to the actual computer. So this allows us to move information from this barrier to the actual computer that requested it. So when we're using port forwarding, we have to have a static IP present because we have to be able to move it from whatever our recipient is to a more permanent connection. So you can't really do it with dynamic IPs reliably. And your computer, unfortunately, will be more vulnerable this way because your private IP address that connects directly to your device will essentially have a direct access point that will be difficult to hide. It can't be what's called obfuscated as easily. So here we can see the different connections moving from the internet to a particular connection. So the 80 connection we were talking about there just a little bit ago on that, the two different people at the little stands, this is kind of a representation of that as well. We have a packet coming in from the internet to port 80, and then that is forwarded through to the web server. So it's just basically saying, oh yes, this is where you need to go. And then this is where we can deal with some of that forwarding. So we have here remote desktop connection using port 3389. We have our beginning and ending ports internally and externally, and what address that is approved for. So we can add that in. This particular router has a drop down for several different services, and you'll learn about the various ports as time goes on for things like FTP, TFTP, NetBIOS, HTTP. There's a ton of ones out there. But in order to forward that, you have to make sure you're giving the right port number. So here we can see that we've got kind of a firewall situation with forwarding to be able to receive information from an outside source and then move it directly to whomever needs to receive it. So we talked about the DMZ, basically just the space between two firewalls or from an internal and external device. Content filtering is also able to be done. You can filter things based on their type of content. So you can draw from, again, blacklists or whitelists. We can do it based on particular computers, particular users, categories of websites, individual websites themselves, keywords, services, time of day, time of week, whether or not we allow certain types of multimedia. Maybe we don't allow things like Flash because Flash has a lot of security vulnerabilities. So here we have the Netgear Genie allows us to filter things by domain names, keywords, things like that. So setting up a wireless network is not much different than setting up a wired network, except for the fact that we have to determine the frequency bands that we're going to use based on what type of modem and what type of interface card we have, and then making sure that we have the right credentials. So Frequency bands for Wi-Fi have changed over the years to try and improve the amount of speed that's deliverable as well as the range of coverage that is given. So 802.11a and b came out at roughly the same time. 802.11a ran up to 50 meters of coverage and had a radio frequency of 5.0 gigahertz. 802.11b ran twice that distance but was at half the frequency, a little bit less than half actually, because whenever you have frequencies, if you cut them in half or cut them in quarters, you get what's called a harmonic, and that means that there can be overlaps of the signal, which could cause potential issues. So you try and avoid that. With the 802 standards, the further the distance that was covered, the slower the speed. So for 802.11b, even though it covered 100 meters, it was only about 30% of the speed of what you'd experience with 802.11a. So in certain cases, you had to kind of decide, did you want to cover a larger area or did you want to have a slightly faster speed within that area? 802.11g tried to combine both. So 802.11b was now going to have faster speeds. So we had the same coverage range and same frequency, but we were faster speeds. 802.11n started using what was called dual band, to where you would have 2.4 5 gigahertz, and then 802.11ac all the way up to, I believe they're up to like 802.11q or something similar to that now. What's called Wi-Fi 6. So there's several options that are very similar to that. So here we have a 2-antenna wireless network adapter. This uses QoS techniques like beamforming, being able to prioritize information using a process called MIMO, multiple input, multiple output. So it's able to focus more energy on one antenna than the other in order to prioritize devices by their physical location. Now, in order to secure a wireless network, we traditionally need what's called a key or a passphrase. This is the most common method of securing a wireless network. Now, this can be broken, but it is a pretty easy way of going about it. So imagine that you're at your house and you need to be able to prevent somebody from being able to get inside the door. Easiest way is just to lock the door, right? So you turn the little deadbolt lever and that's it. But if somebody has the correct key, they can get that deadbolt open. So the complexity of that is going to be whether or not it uses a particular type of encryption, how complex the key is, usually by length. The router firmware may be able to allow access to a guest network. It may have what's called a fail secure option, to where essentially if the network is being assaulted by attempts to use the incorrect passcode, it may lock the person out for a given period of time. It may temporarily block their MAC address, etc. Now, it is best to enter a security key different than the password that you use to get to the router utility, because anytime you reuse a password, you're making it more vulnerable to somebody trying to break it open. Because human beings intrinsically are a little bit lazy, and they don't necessarily want to generate new passwords every time they access something. So there's a lot of password reuse that goes on, which means that attackers are going to be looking for that, and automated tools will be able to look for that as well. Now, our main standards for 802.11 networks are things like WEP, which we don't use anymore because the key used for the encryption is static, which means that it's able to be broken fairly easily. So do not use WEP, do not use WEP, do not use WEP. WPA is okay. WPA2 is a much more common standard, and then there's WPA3, which has some additional features but has not been widely adopted to the same degree as WPA2 yet. But it really is just kind of a matter of time. Now, some other things that we can do to try and secure the network is, of course, to change the default SSID or broadcast name, SSID standing for Service Set Identifier. And we can turn the SSID off. Now, we can treat this as just kind of a deterrent, because there is software out there that can discover an SSID that is not being broadcast. But it is just, again, it's a way of slowing things down. You know, if they don't see that a particular network is there, they are less likely to try and go after it. The channels for the wireless LAN, there's a specific sub-frequency within the main frequency of the transmission that is used to avoid collisions and interference. So if you're having issues with a channel, let's say you're set on channel 3, go ahead and jump up to like channel 5 or channel 6, and see if that gives you any difference, because somebody else in your immediate physical space may be using that same frequency. Some APs actually allow you to adjust the power levels of your radio to reduce interference. You can artificially reduce the range of your network. So if you're concerned about privacy, like if you're in an apartment and you don't want your Wi-Fi network to be accessible from the street, you can actually back that up. And you can also save a little bit of electricity that way, because there is a requirement of being able to pump in a certain amount of voltage to be able to make your AP send out that signal over a given distance. So here, of course, we can see an example of a Linksys router that has some variations like we talked about here, whether or not we're using 2.4 or 5 gigahertz, whether or not the SSID is broadcasted, what channel it uses, etc. Now, wireless QoS usually requires what's called WMM, Wi-Fi multimedia. Excuse me. And we can prioritize different types of information based on their content. So video could be prioritized over audio or vice versa. WPS, not a process I particularly recommend, because there's a lot of little security holes if you don't manage it correctly. This will go ahead and generate the SSID and security key for your network based on a random string of automatically generated numbers and letters. Now, if we have a situation where somebody keeps trying to spam the WPS connection, we want that to fail securely. So if somebody keeps trying to use it, we'll just allow it to cut itself off. So if somebody tries to hook in the pin, then they'll be like, okay, nope, you obviously do not know your pin, so we're going to go ahead and block this for a certain period of time. If you take net 125, we talk about blocking a certain amount of attempts for a certain amount of time. Now, if we're having issues with our network, we have a couple of different ways we can work with that. There's a couple of different tools we can use. Ping, ipconfig, nslookup, traceroute, net, which has several different subcommands we can use, things like net stop or net service, and then net stat, which is a little bit different. You'll notice that net here, where it says two net commands, is a single word, whereas net stat is a conjunction of two words. So in the title bar here, I'm going to give you the parameters. So we can see ping -a-t and then whatever your target name is. This allows you to send an echo request to a remote computer that will sometimes give you a reply if configured correctly. This allows you to figure out how long it would take for a certain packet to be able to move between those two computers, or whether or not that computer is even responding. If you're using something like looking up a website like Google or Cisco or CNN, that will actually test whether or not your DNS is working, which is something occasionally you will have to go in and verify. So here we have some examples. We've got ping 6932.208.75. This is going to ping a particular IP address. If you use the -A flag, that tests for name resolution. -T essentially is what we call the infinite ping. It'll keep pinging until we turn it off. We have to use Control C in order to stop that. If we ping a loopback address like 127.0.0.1, this essentially tests our local TCP/IP stack to make sure that the internal stuff seems to be working, that it goes through the normal process. It's kind of like checking to make sure your wallet's in your back pocket. If you pat your pocket there and you don't feel your wallet, then obviously you know that something's up. So it's just a way to make sure this isn't something external, this is something internal. ipconfig, that gives us a number of different internet protocol configuration issues for certain interfaces. So we can see things like /all, which shows all of our different network configuration information. Release, renew, display, and flush DNS. These allow us to modify an address that may not be behaving. NSLOOKUP, this allows us to test name resolution problems. So that's where that NS comes from, is namespace or name server. Zone data for a DNS server is the portion of the DNS namespace that the server knows about. So when we're trying to find excuse me, a particular website's IP address because we're having trouble connecting to it through using the domain name that it was given, what's called its FQDN, fully qualified domain name, we can then retrieve it that way. So we can use these reverse lookup processes. So here we can see NSLOOKUP Microsoft.com. We've got our public DNS, and then we've got our non-authoritative answer giving us some information about the publicly accessible IPs for this particular site, whatever it is. So here we've got 5 different addresses. Trace route or trace RT, depending on who you talk to. This is useful when trying to figure out a problem when you're having issues reaching a destination host. So, the connection seems to be good, but you can't get to this particular website without having some issues. Well, trace route is like ping, except it keeps track of the movement from one place to another. So as you go from one source to the next, it actually keeps track of how long it takes to get there, as well as whether or not it was successful in arriving. So it gives us what's called a TTL, time to live, and then as that packet moves from one location to another, that TTL decreases. We have to have a value like this because we don't want to create what's called an infinite loop or an infinite packet traversal. So essentially, as the packet moves from place to place, you want it eventually to expire so that way those packets don't just float into nothingness and congest the network. So here we can see a trace route command going from Ms. West's computer to the Cengage website. And we can see here that the known IP address is 69.32.208.75, and we're going from her local network to these different charter branches here. We're going from Texas to South Carolina, moving around. Now we're in Cincinnati, moving around again, and then here, boom, we hit the usstore.cengage.com. So we can see that there's these time loops, these different addresses that it's moving to. Now, if we run into a situation where you can see something like a request timed out, if we see that happen, and it does it pretty much throughout the entirety of the communication until the TTL dies, then we can assume that that is a point at which this particular network transition is not allowing routing to complete. So that would be a point at which that communication path was failing. Now, I brought up net a little bit earlier about being multiple commands. Net is kind of a pre-command, if you will, and it requires a second parameter in order to give you a particular connection and allow you to complete a particular command. So net use allows you to connect or disconnect a computer from a shared resource. You can substitute one connection for another. You can route information from, an Ethernet connection through a dial-up connection as far as like passing information that would normally be there. This is something that you see a lot for older hardware. If you have to connect via a COM port that is not traditionally used, you can actually use a USB or Cat5 connection as that connection instead. So for example, in order to pass a username and password to the blue light remote computer and then map a network drive to the medical folder on this, we would use the net use, giving the username and password, and then we would type in net use Z to establish a network drive mapped to the letter Z using that particular folder. That's a very simple example. There may be more complex ones that you would experience, but that's the same general idea. And then there's also net user. So if we add an R to that, that allows us to modify user accounts. Again, what you notice is that these are things that we probably could do in the Windows GUI, but the difference is if we do this in command line form, this allows us to script things and to automate them so that way we can make sure that we handle multiple users correctly at the same time. Net stat, which is not the same as net space stat. I'm not even sure if that's a command, I don't recall. But this gives you network statistics about the activity and parameters of your various network connections. So if you have curiosities about, whether or not a particular connection is giving you what you need, you can output that to a file. You can check to see whether or not certain programs are using a connection that shouldn't be. You can see process IDs, etc. So that is chapter 7. Does anybody have any particular questions or concerns about what we've just discussed today? Okay, good.